YouTube freaks, we're going to be going over the gradient tree boosting algorithm. All right, and I got really loud there at the end because I don't know, just want to put more bravado into my voice because you know how it is. So I'm going to spell it out. Gradient. And I know there's a few of you that are gradient freaks. A gradient is a derivative. Basically, it's a partial derivative. It's just has to do with matrices and whatnot. But we're going to be walking through each step here, and I'm learning along with you because this is the first time I'm kind of making sense of this. But we'll pretend I'm a pro, right? I'm going to turn on some light here. I'm a big believer in seeing things, even though my screen is backlit. Yeah, there we are. That's the magic right there. That's the warm light that I so do desire. Okay, so we have step number 1. Step numero uno, which is initialization. And this is important because your starting point, or sort of like your starting model, your baseline model is the constant function. You know me, I get a little excited. I start talking about the gradient even before I write down the argument here. I want to kind of make that a little more pretty here. There, that's pretty. I mean, that's nice. You guys let me know if that's pretty or not. I think that's beautiful. So we have this right here. Yi. Of course you have. Is it consistent? Semi. Okay, so we have our constant function. So mathematically, this right here is a constant, and it's chosen to minimize the overall loss, which is L. This is loss. Okay? So when applied to every data point, xi, yi, okay? And so I guess, for instance, if L is your squared error loss, then your little thing here would be the average of yi. And if L is your logistic loss, then this thing, I gotta find the name for it. This is embarrassing. Can I just call it, I should probably, let me AI this real quick. What is this? What is it called? What is this Greek symbol called? Do you know what this one's called right here? This one.
I think it's gamma.
Gamma. Yo, someone much smarter than me just said it's gamma, and you know I'm listening.
You should probably Google that.
She's also a lot prettier than me, too. Wait, give me a second. Gamma. If she's right. Greek letter. Oh, you're right. I have to give her $5 billion now. We had a bet on it. So it's gamma. Again, shows you how much I know. So if L is the logistic loss, then gamma would be the log odds that minimize the deviance. So you kind of get what I mean here. So you're defining your loss and then your gamma respective to it. Okay? Obviously, this process is iterative. You're starting at this. This is your start point. This is not your end point. It's a machine learning thing, okay? Algorithm, probably the best way to describe it. So it's just the baseline. So now we can start talking about the boosting iterations. So we'll repeat the process below for m equals 1 to big M, where big M is the number of boosting rounds or trees you plan to build, okay? So now we can start talking about computing your pseudo residuals, which, I was so eager to talk about earlier, and now I get to talk about them now. This is what it is. And build our little thing here. I and f of xi. Don't mind me. This should look semi familiar. If you're doing this stuff, then you've already seen gradients. You've seen things akin to this. You've probably seen the lasso or the ridge where you're using gradients and sort of gradient descent even. Now, obviously, this wouldn't be that, but it's notationally similar probably. So for each data point I, boink, pointing at I, you calculate the negative gradient of the loss function at the current model, which is f at m less 1 of x of I. So this is called a pseudo residual because of certain loss functions like squared error. It literally is the residual, right? And so this would be, if it was for squared error, it would literally be I'm writing it out all carefully, right? So for others, like logistic loss, it's the negative gradient of the loss, which plays the role of a direction for improvement. So the whole point of this is boosting is about additively correcting the current model. So you're making those little corrections here. And by using the gradient of the loss, we know which direction to move the current model, right? To reduce the overall loss. So again, conceptually, it's like, okay, well, at x of I, how should I tweak the prediction to reduce the loss? All right. Our next part here is we're going to fit a regression tree to the pseudo residuals. Okay? So fit a regression tree to the targets. So this is your target right here. And you produce the terminal regions. So your big R, J of M. And J can equal, obviously, 1, 2, ... J of M. Okay? So you use these newly computed pseudo residuals, which is that right there, as the target values in a regression tree. So in other words, you take your input features, x of I, and their pseudo residuals, RIM, and train a tree that predicts RIM for xi. And the tree partitions your feature space into terminal regions, which are also known as leaf nodes. So that's what we got kind of going on here. So why this step? So a regression tree is a flexible way of approximating a function. So the idea is that the pseudo residuals can be approximated by the tree's piecewise constant predictions in each leaf. And this tree effectively captures how you should adjust your current model based on X to reduce the loss. And again, your current model, because if it's not already obvious enough, I'm just reading this, is this, but I translated it darkly in my head. I would say your most important part of learning this would be to understand what each part means. That's why I'm kind of going over this slightly slower, where I'm like, oh, well, this is loss, this L is loss. I feel like with machine learning, it's a lot more important not to know the math, but to know what each thing in the math is supposed to do. And so definitely take most of your time learning the conceptual and not the math, because the math is fairly easy or just done by computer. It's just done by computer. Let's be so for real here. You're not doing machine learning in your head. Who do you think you are? If you're doing machine learning in your head, I would like to meet you. We gotta have a coffee date, okay? you just hit me up, right? You DM my YouTube channel if that's even possible. I'm kidding. Don't do that. I'll be scared of you. Please don't find a way. This is in, by the way. This symbol means like in. It's the best way to understand that. It's like in the space. Most of y'all will already know that. Some of you won't. That's too bad. And I hope this isn't bugging you too much. I'm just taking my time here. I want to make sure everything's correct for this next part, which I will be going over in just a moment. Okay, so this is your you're solving for the best leaf values. So if you don't remember, the whole point of this was to minimize the loss. And so you got to find the best leaf, right? Because you are using a machine, and you might find that sometimes it does something great and then other times it does something bad. And I think that a great way of kind of explaining this is, well, even just by using AI. Say you're using like chat bots, sometimes they'll like hallucinate crazy stuff, and well, that's rare, but you know, it happens on occasion. So who knows what's going to happen here. Anyway, so each leaf, which is the region here, this is region, so gets a single value, which is gamma j of m. That value, gamma j of m, is chosen to minimize the loss if you shift the model's prediction for all x of I in the region rj of m by gamma j of m. So you're starting to see how it all comes together. Note that the current function, f of m less 1 of x of I, is the current model's prediction. We add gamma to it to make a new prediction for points in that leaf. We pick whichever gamma yields the best performance in the loss, right? So there are going to be different gammas to best improve the loss, to lessen the loss. Right? Once you have the structure of the tree, which is the partition, you need to decide how much adjustment to apply in each leaf. This ensures that the update from iteration M is as beneficial and, you know, as loss reducing as possible. As loss reducing as possible. And then one of the, I guess, final steps here, right? You're waiting for this one. You're on tenterhooks. That was correct. I was going to erase my F. Is, of course, updating the model. So I'm going to write it all down here. Again, maybe it's best for me to, but hey, you know what? This is obviously the updated, and this is the current, or I guess like the previous, because now you've got this new model where you've chosen your best leaf. You've chosen with your gamma that reduces your loss the most and is obviously inside your region. And like Bob's your uncle or whatever. Come on now. I mean, you know the way the story goes. And I say Bob's your uncle just the perfect amount of times. Okay, I'll tell you that much. Yeah, I say it like 1,000 times, but like whatever. So what does this mean? So the new model, f of m, is the old model, f of m less 1, plus the piecewise constant correction from the newly grown tree. So the indicator function I, which is, you know, function of x, which is in your region rj of m, ensures that you add gamma only if x falls into the region rj of m of the new tree. That is important. Needs to exist in your region. So why is this step important? So boosting is an additive approach. So each new tree tries to correct errors as measured by the pseudo residuals that the previous model f of m less 1 was making. By repeatedly updating f in small steps, so one tree at a time, you gradually reduce the loss and improve predictive performance. So your final model here, and this is going to be I guess maybe the easiest part, but you gotta love it. You gotta love it. You know what the hat means. You know the hat means we're almost there. You're almost home. So after M boosting rounds, we already went over capital M. It's all your, maybe I'll scroll up and talk about it. Boop, boop, boop. Yes, so capital M is the number of boosting rounds or trees you plan to build. So this is your grand finale. Okay, after boosting the amount that you wanted, the final model is simply the last updated function f of capital M. This model is typically used for prediction on new data. So why this step? So you stop once you've reached your chosen number of trees, or a stopping criterion like validation error. And so now you have a final predictive function that hopefully generalizes well without overfitting, especially if you use regularization or early stopping. Regularization. That is a fun word. Everyone say it with me. Regularization. Wow. Or early stopping. I kind of like early stopping better because I can say it. So to put it all together, to summarize what we did, so you start with a simple best constant model. You compute pseudo residuals, the direction in which you want to improve. You fit a regression tree on those pseudo residuals, partitioning the input space into leaves. You compute the best leaf value so that adding them to your model decreases the loss the most. You update the model by adding the tree's contribution, and you repeat for the desired number of rounds or until some stopping condition. So it's about nudging your model toward better predictions by following the gradient of your chosen loss function. So each tree is fit to the current mistakes, pseudo residuals, of the ensemble so far. And this gives a pretty good framework to be applied to different tasks, obviously being, regressions, classifications, ranking, etc., simply by choosing the appropriate loss function and repeating the above steps. All right, I'm done explaining this because I don't understand it that well myself, but I hope I did an okay job, and I will catch you in the next video.